Effect of a semi-permeable partition, osmosis. A glass bulb contains argon gas at room temperature and at a pressure of 1 atmosphere. It is placed in a large chamber containing helium gas at room temperature and 1 atmosphere. The bulb is made of a glass which is permeable to the small helium atoms, but not impermeable to the larger argon atoms. Describe the process which ensues. What is the most random distribution of the molecules which is attained in the ultimate equilibrium situation? What is the pressure of the gas inside the bulb when this ultimate equilibrium situation has been attained? So let's look at the scenario here. We have a chamber that contains helium. We insert a glass bulb which contains argon, and helium and argon, they are at a temperature of 300 Kelvin, room temperature. So we have room temperature here and also room temperature here in the bulb, and the pressure is 1 atmosphere, and here the pressure, initial pressure, is 1 atmosphere. So let's describe the process which ensues, and we have to be careful with the fact that the glass is not permeable to the larger argon atoms. So what will happen here? We have a non-random configuration for helium atoms. So helium atoms will start diffusing into the bulb until we attain a completely uniform random distribution of helium atoms. So we can describe this process as follows. Due to random collisions, helium atoms will penetrate the bulb and finally will fill the bulb until a uniform helium gas atom distribution is achieved. So we will have the most random distribution at the end. What is the most random distribution of the molecules which is attained in the ultimate equilibrium situation? So let's clarify what happened in this process in part B. Well, we have the bulb impermeable to argon atoms. So since the bulb is impermeable, and it's impermeable because argon atoms are too big, the most random distribution that is allowed by this setup will be a uniform distribution of helium atoms in the entire volume, which consists of the glass bulb and container, and we will have a uniform distribution of argon atoms inside the pulp. Because the argon atoms were not allowed to diffuse into the rest of the environment in the container, since the glass is impermeable to argon. What is the average pressure of the gas inside the bulb when this ultimate equilibrium situation has been obtained? So I would like to note that we see in the problem statement both gases were at room temperature. So we have thermal equilibrium between the gases. So thermal equilibrium is reached. We won't have energy transfer in the form of heat. And we know that when we have two gases in thermal equilibrium, the mean energy per atom should be the same. So it will be the same average energy per atom for helium and argon sides. And now I have the number of molecules, the number of atoms, helium atoms, per volume. This is the total volume. So this has the total volume. And then the bulb was inserted. So the number density is the same initially and finally, because then it will diffuse into the bulb. And so let me call this initial configuration, and this is the final configuration. In the initial configuration, I have a uniform distribution of helium atoms in the entire container, and also in the final configuration, I have a uniform distribution of helium atoms in the entire container, including the bulb. So this is the same initially and finally. Okay, so if I look at the pressure, the partial pressure of helium, which is 2/3 the number density of helium multiplied by the mean energy per atom for helium, because epsilon bar doesn't change, n doesn't change, the partial pressure of helium will not change. So that means the pressure of helium in the final configuration will also be 1 atmosphere. Now I look at the pressure of argon, the average pressure of argon. It is 2/3 number density of argon and mean energy per atom. Now in this experiment, since I don't have heat flow, neither the mean energy per atom for argon or the number density of argon is changing. So this is at thermal equilibrium. So we're not changing mean energy per atom by heat flow, or we're not changing the number of density, the number density for argon atoms. So the pressure of the argon gas, the partial pressure, will be 1 atmosphere finally as well. So inside the bulb, what will be the total pressure? We have the pressure, a partial pressure of helium plus the partial pressure of argon which is 1 atmosphere plus 1 atmosphere, the answer will be 2 atmospheres for the pressure inside the bulb. So what is the average pressure of the gas inside the bulb in the ultimate equilibrium situation? So that's our answer. So just to recap, we have a glass bulb containing argon gas at room temperature and 1 atmosphere pressure. It is placed in a large chamber containing helium. So helium was already in the large chamber. It has room temperature and 1 atmosphere pressure. The bulb is made of a glass which is permeable to the small helium atoms but is impermeable to the larger argon atoms. So it's acting like a filter for the different types of atoms. Describe the process which ensues. Well, we have a concentration gradient for helium that is not a good random distribution, so we need to attain the most random uniform distribution at equilibrium. Since the helium atoms are allowed to permeate the glass, they will fill the glass bulb until we have a uniform distribution of helium atoms everywhere. What is the most random distribution of molecules in the ultimate equilibrium situation? Well, the helium atoms will fill the glass bulb until we obtain a uniform distribution of helium atoms entirely in the container. However, since the argon atoms cannot go through the glass bulb, they will be filling the glass bulb and forming a uniform configuration inside the bulb only. So we will see that uniform helium atoms in the entire container, uniform distribution of argon atoms in the bulb. Okay. And in part C, what is the average pressure of the gas inside the bulb when this ultimate equilibrium situation has been attained? Both gases were at room temperature, so we have thermal equilibrium. That means mean energy per atom will be the same. The number density for helium atoms is the number of helium atoms divided by the total volume initially and finally, because it's also filling the entire volume finally. So we have the same number density, same mean energy per atom. So 2/3 number density times mean energy, mean kinetic energy, gives us the mean pressure from elementary kinetic theory, and that is 1 atmosphere. It's not changing. We also did not change the number density of argon, the same number of argon atoms in the same volume, that is the volume of the glass bulb. The mean energy is not changing because we have thermal equilibrium. There is no heat flow between the two gases. So the argon partial pressure will be 1 atmosphere finally also. So inside the bulb we will have helium plus argon partial pressures, which is 2 atmospheres. So the effect of a semi-permeable partition is to have a build-up of pressure inside the glass due to which is driven by the concentration gradient for helium atoms. So when the helium atoms fill in the glass bulb, but argon atoms are not allowed to escape from the glass bulb, we have a build-up of pressure, and the final pressure is 2 atmospheres.